Welcome folks, in this section we're going to introduce something called the harmonic oscillator. That's the model that we use when we study springs. So we've been studying nth order linear ODEs, and we're going to specifically look at second order linear ODEs here, and we're going to consider them as applied to springs. So we're going to look at each of the individual components of this model, but let's put the whole thing up here. Here's our spring mass model. It is mx double dot, and that stands for the second time derivative, plus bx dot plus kx. Let's see, kx is equal to some forcing function f of t. So I said it, but let's just remind ourselves, this x dot, specifically the dot, refers to the time derivative. So that it means when you see x dot, you can know that it specifically refers to dx, dt, because it's a time derivative. This isn't essential in our class, but in problems where you might have multiple independent variables, that dot notation specifically refers to the time derivative. We'll see why this is in a second, but let's go ahead and put some conditions on here. Here we assume that b and k are greater than or equal to 0, and that m is greater than 0. Okay, so let's look at the individual components of this model. We have our mass here. Mass will either be measured in kilograms or perhaps slugs if we're using the imperial system. So we've got mass here. We just said that this is the second time, well, this is the second time derivative, so this would be acceleration. Here we've got B. B is going to be our dampening force, or our drag coefficient. X dot is the first time derivative, so that's velocity. K is going to be our spring constant. We'll talk about that in the next bullet. And we've got X, which is our displacement. And then finally, we have our external forcing function, which may be 0. In a lot of our problems, it will be 0, but later we'll see how to work with our spring mass problems when we don't have a 0 external forcing function. Okay, so that's a lot. Let's go ahead and first examine each of the components of this model, and then we'll derive this model later on in the video. So the first thing we want to talk about is Hooke's law. And Hooke's law says that we have that when we stretch a spring with a negligible mass, that spring is going to exert what's called a restorative force on that spring. So it's a restorative force. And you should think about that. If you've ever stretched a spring, you know that when you release the spring, it wants to go back to some sort of rest position, as long as you don't overstretch that spring initially. And so Hooke's law says that restorative force is proportional to the distance that the spring has been stretched. Usually we measure that as from the rest position. Okay? So since this is a restorative force, it's in the opposite direction of the spring, in the opposite direction that the spring has been stretched. Therefore, Hooke's law, so we're just practicing that. I don't know Hooke, but this is his law. And Hooke's law says that the force restorative in a spring is equal to negative kx. Notice that's exactly what we wrote right here when we said that it is proportional to the distance the spring has been stretched, and it will be opposite. So if I'm saying that k has to be greater than 0, when we give the force restorative, you'll see it written with this minus kx. Folks, at the end of the day, make sure that your model works out this way, and that m, b, and k, when they are presented in this order, are all positive. I don't want to get too far into the weeds with working with these negative signs here. It's easy to do that. Let's just give this a name. We've set it right up above here, but this is called our spring constant. And I will either give you this spring constant in a problem, or I'll give you enough information to figure it out. So this is our spring constant. And it'll either be explicitly stated, or I'll give you some pieces of information, some initial states, so you can figure out what that is. And we'll see how that works. Okay, so now we want to talk about that dampening force. So an object in this class, for an object in motion, we'll sometimes assume that there is a dampening force. And we should think of that as something like friction, something that's slowing down an object that's currently in motion due to interacting with the surface that it's moving on, or if it's passing through air, interacting with the air particles. So we'll just summarize all that together in a math class and call that the dampening force due to some sort of friction. Unless otherwise stated, this dampening force is assumed to be proportional to the velocity of the object. And opposite the direction of motion. So another way to say that is that our dampening force, I'll label as force D for dampening. I guess we'll keep capital since we're there. Force D for dampening is equal to, so it's proportional to the velocity. So we would have K. We don't want to use K though. We should use something else. Let's use, I think we're using B in our model. So K or B times our velocity. How do we denote velocity? We're going to denote it as the first time derivative of position, and we said that it's opposite because in our model, as I'm setting it up, we're starting with saying that the B value can be greater than or equal to 0 but not negative. If we want this to be opposite direction of motion, we'd have to have a minus sign there. And in general, you should think of this B, this is our drag coefficient, it's sometimes called. And you should think of this drag as being small when we're on slick surfaces, surfaces without a lot of friction like ice, and large for rough surfaces like sandpaper, or if this spring is oscillating in, rather than oscillating up and down in air, it's oscillating up and down through a viscous fluid like oil or something. Okay, so then we can have, in some cases, we'll have an external driving force. So let's go ahead and draw a picture here. Here we might have, a spring mass system. And this spring could be, we could put an initial stretch to this spring. We could have it start with an initial velocity. But in this case, what I'd like to do is let's actually assume that this wall could move back and forth. So if this wall can move back and forth, we would think of that as an external driving force. And we'll study those problems, and they will be kind of the most interesting ones when we get a little further on in this model. Okay, so let's go ahead and derive our simple harmonic oscillator equation. So the name of this model is the simple harmonic oscillator. And I would say that this model is just that, it's just a model. We are taking into account the drag coefficient, which is the drag of this system as it's oscillating back and forth. I feel like that's pretty realistic. We've got our mass and acceleration. We're going to use Newton's second law to derive this, but it is still just a model. There are some assumptions that are made. But let's go ahead and start off. So as I recall, there's a Newton's law. I don't remember the number, but one of Newton's laws says that mass times acceleration is equal to the sum of all the forces. So let's go ahead and actually iterate these. We'll call them from I equals 1 to n of I if we had, say, n forces that we've got acting on this object, and the sum of all of those is equal to the mass times acceleration of the object. So let's go ahead and put this in terms of what we've just been discussing. So we're going to denote acceleration as x double dot. So there's our mass times acceleration is equal to the sum of these forces. And we're going to go grab all of these forces that we've listed. We've got our external driving force. I should say that we usually use for this external force, we usually use the notation F of t for that external driving force. And I think that's what we did up here. So if we add up all those forces, what do we have? Well, we had our restorative force from Hooke's law, so that was our negative kx. Remember that Hooke's law says that the restorative force is proportional to the distance that the spring has been stretched and in the opposite direction. And then we also had the drag force, which is equal to which is proportional to our velocity and in the opposite direction. And then we had our external driving force. So the next thing to do to make this look like our model is just to take all of the dependent variable terms over to the other side, leaving the non-homogeneous term here, f of t, the forcing function, over on the right. So when we do that, we've got mx double dot plus bx dot plus kx is equal to f of t, and there is that model. As you're building these, folks, try your best to work with the signs appropriately. At the end of the day, when you get to this model here, each one of these coefficients, once it's written in this form, this coefficient needs to be greater than 0, this coefficient needs to be greater than or equal to 0, and this coefficient should be greater than, I put greater than or equal to, but all of these coefficients cannot be, none of these coefficients can be negative when we've got it in this form. So that's sometimes confusing for students. You're trying to derive what k is. Maybe you've somehow mismatched your orientation as to what's downward, what's upward, or what's left, what's right, and you've mismatched that orientation, and you get to this model right here. And if k comes out to be negative, it is likely just a sign error, and you should ensure that all of these coefficients are non-negative. All right, that's a good starting point. I'll see you in the next video.